In this lecture, I'm going to talk about representing a homomorphism in terms of a matrix. We'll do both examples of where the bases for the domain and codomain are the standard bases, and we'll also do some examples where they're not the standard basis. I have a little bit of notation to mention here. We're going to use column vectors to represent vectors. That'll become apparent when you see the examples. And when we use the standard basis, we won't have any marking. We'll just show the column vector. But when I use a non-standard basis, I'll put a little subscript showing what basis is being used. You'll see what I mean when I get to the examples. I just wanted to point it out here first. So remember, the homomorphism is a linear transformation. And what we're going to show in this lecture is that we can represent a linear transformation in terms of a matrix. We're going to focus on finite dimensional vector spaces. So both the domain and the codomain of the homomorphism will be a finite dimensional vector space. We'll start with an easy example. We'll have easy in the sense that we're going to use the standard basis for both the domain and the codomain. So here's our homomorphism. It's taking a vector x, y, and R2 and mapping it to this vector here. And as I mentioned, we're using the standard basis for both the domain and the codomain. I'll leave it as an exercise to verify that this is a linear transformation, in case you want to practice your understanding of that concept. So my claim is we can represent this linear transformation this way here as A times xy, the column vector xy, where A is 2, 1, 3, minus 1, 2, 1, 3, minus 1. So I'm just taking the coefficients from our definition here. Let's check to see if that actually works. We'll check by taking an example. So we'll use minus 2, 2, and compute it using the original definition and then using the matrix multiplication. Okay, so if we put minus 2, 2, and we plug minus 2 into for x, and plus 2 in for y, we get this here. So we get minus 4 plus 2 is minus 2, minus 6 minus 2 is minus 8. If we use matrix multiplication, we have 2, 1, 3, minus 1, and then we multiply it times minus 2, 2, so we get 2 times minus 2, it's a minus 4, 1 times 2 is 2, that's minus 2, and then you get 3 times minus 2 is minus 6, minus 1 times minus 2 is minus 2, minus 1 times plus 2 is minus 2, and then you get minus 8. So we do get the same thing here. The situation gets a little bit more complicated when we don't use the standard basis in either the domain or the codomain, and I have an example of that on the next slide. So we're going to use the same linear transformation that we did in the previous example. I have it written down here on the bottom just so you don't need the page back. However, what we're going to use are different bases. We're going to use the basis S here for the domain and the basis T for the codomain. So the procedure for computing the transformation matrix is a bit different. We first just map S to the codomain using our linear transformation. So we take 1, 1, and that maps to 3, 2. Then 1 minus 1, and that maps to 1, 4. And these are in the standard basis. 3, 2, and 1, 4 are in the standard basis. So we need to convert those to the basis in the codomain. So we write 3, 2 in terms of 1, 0, 1, 1. And that would be, if you take 1 times this and 2 times this, you get 1 plus 2 is 3, and then 2, when you take 0 plus 2 times this, so you get 1, 2. I mean, if you really wanted to work this out, it would be 2 equations, but I'm just giving you the answer and then kind of giving you a verification here. And then the 1, 4, if we write that in terms of these two here, it would be minus 3 times the first one and 4 times the second. So this would be 4, 4, and then minus 3. And that would, when you add them together, you get 1, 4. So now we have both of the outputs of the basis vectors in the domain written in terms of the codomain. And in fact, that's what we use in our transformation matrix. So we take 1, 2, and minus 3, 4, and put that in our matrix here. And that'll give us a representation of this linear transformation in terms of these bases. So let me show that in terms of an example on the next slide. So let's use minus 2, 2 again as our test case. The first thing we want to do is, since we're working on two different bases, which I copied down here so you don't need to page back, S and T. So this is the basis for the codomain. So first thing is we need to represent minus 2, 2 in terms of S. And if you take 0 times the first one and then minus 2 times the second, you would get minus 2 plus 2. So this is the representation of this in terms of the basis S. So we plug in, doing it the first way using the transformation here. We plug in minus 2, 2, we get minus 2, minus 8, which we know from before, but we're working in these different bases. So we want to write minus 2, minus 8 in terms of T, and that would be 6 times this minus 8 times the second term. So you'd get minus 8, and then plus 6. And that would, when you add those two together, you get minus 2, minus 8. And we want to show that if we take our matrix B, which I've copied from the previous slide, and multiply it times our input, but written in terms of the basis vector S, which I've shown here, that you'll get an output in terms of the basis T. So you have minus 1 times 0 is 0, of course. Minus 3 minus 2 is 6, and then you get 2 times 0 plus 4 times minus 2, and you get minus 8. So you do get the same answer, and doing it either way. And what I want to do next is formalize what we've done here. So let's formalize the notation for the concepts we discussed in the previous two examples. Let V be a vector space of dimension n with basis S, and W a vector space of dimension m with basis T. Let F be a homomorphism, linear transformation from V to W. Next, we represent the mapping by F of each basis element of S in terms of T. We write it this way here. So the representation of F of S1 with respect to T is this column vector, and we do that all the way up to S sub n, because we said there's n elements in the basis. If we put the column vectors together, we form what is known as the matrix representation of F with respect to bases S and T, and that's this matrix here. And you notice the notation here, rep S comma T F. So S is the basis for V, T is the basis for the codomain W, and this is basically the matrix we computed in example 1, although it was very simple because we were going from the standard basis to the standard basis, and then we did the same thing in example 2, but we had non-standard bases. Okay, so that's the procedure and the notation. And as we've shown, at least through an example, this gives you the same effect as the linear transformation when you multiply this times a vector but we haven't proven it yet. So that's what we'll do in the next theorem. We'll actually prove that this always works. So let's go ahead and prove what we've been saying. I put it in the form of a theorem here. If A equals rep of S with respect to S and T is the matrix representation of a homomorphism from vector space V of dimension n with basis S to vector space W of dimension m with basis T, then the mapping of a vector V, an element of vector space V, by F is given by the product, the matrix A times V written in terms of the basis S, and that equals W in terms of the basis T. So in order to do the proof, we start with taking any vector V from our vector space V, and we write it in terms of the basis S here. It's a column vector. So again, what this means is that V equals V1 times S1 plus V2 times S2 plus ... Vn times Sn. And keeping in mind the V1, V2, Vn are just scalars. Next, we represent the mapping of each vector in S in terms of T, the basis for W. So there's m terms here. So f of S1 is this linear combination. This is just notation. F of S2 all the way down to f of Sn. And what I wanted you to notice here is the matrix we wrote down on the previous slide, which I've copied here, is populated in this manner. The FS1 makes up at least the coefficients from this make up the first column. Coefficients from here make up the second, and so on. And these coefficients make up the nth column. Okay, so let's continue. So continuing with the proof, we want to evaluate f of v. And on the one hand, it's a linear. Remember, this is an element of w. So on the one hand, it's a linear combination of the vectors, the basis vectors for t, which I've written here. And then on the other hand, we can substitute in v. This is just from the column vector that we wrote on the previous slide, so it equals this. And then since f is a homomorphism, we can bring out the scalars v1, v2, all the way up to vn. So we have this expression. Then the next step is we wrote each one of the, if you recall the last thing we did on the previous slide, we wrote f of s1, f of s2, all the way down to f of sn in terms of the basis vectors for t and t. So I just plug that in here, here, and here. And then the last step is we identify this side with this side here. So we need to collect all the coefficients of t1. So that would be v1 times a11, v2 times a12, or keep going, and then the last one would be vn times a1n. So the coefficients of t1 on this side of the equation has to equal w1, and then we collect all the ones associated with t2. So that would be v1 a21, v2 a22, all the way down to vn a2n. And then of course we keep doing that, and we equate them with the left-hand side. So we have the two representations for f of v. On the one hand, it's w1, w2, w all the way down to wm. We can put that in a column vector, and then we can represent this right-hand side as matrix multiplication. This is the matrix A that we've been discussing, and this is just v, the vector v. Is written in terms of the basis S. So if you multiply this times this, you notice you get the first equation. W1 equals A11 times V1, A12 times V2, all the way down to A1N times Vn, and so on. So that proves our theorem. We have W is represented in terms of the basis T equals A times V represented in terms of the basis S. So in every case, if we have a homomorphism from one finite vector space to another, using the procedure that we've talked about, we can create a matrix that will map give us the same output as applying the linear transformation. The first slide I already mentioned, so I won't go over that again. The opposite of theorem 38 is also possible, and that's theorem 39. So if we're given a matrix, then we can use that matrix to represent a homomorphism between two vector spaces, and we can select any basis we want for each of those two vector spaces. So let's prove that. Assume that A is of dimension m by n. In this case, the dimension of the domain, called V, needs to be n, and the dimension of the codomain, call it W, needs to be m. Let S be a basis for the domain and T be a basis for the codomain. And then we define the mapping from V to W as f of V for any element in vector space V is given by this matrix product A times the representation of V with respect to S, and that'll give us a vector in W written in with respect to T. And the A is just the m by n matrix that we're given. So what we need to prove is that F is a homomorphism, that it's has this linearity property. So we take U and V and two scalars in R. Then we evaluate F at that. And then we go to this matrix representation. So we just represent U in terms of S and V in terms of S. Then we can factor the A out and the B out. We get this here. But then A times the representation of S with respect to U is F evaluated at U, and A times the representation of V with respect to S is F evaluated at V times B. And so we have the linearity property proven here. Okay, so we'll do an example just to give you the feel for going in this direction. Is fairly easy. You already have your vector A, and it's a matter of selecting your bases and then doing the representation in terms of your bases and just verifying that you have a homomorphism, which we know is true from this theorem. You may be wondering whether the previous theorem holds if there's a dependency among the rows or the columns in the matrix A that we start with. And in fact, it still does hold. The key idea is that the matrix represents a linear transformation between vector spaces of appropriate dimension, regardless of whether the matrix is a full rank or not. Appropriate dimension is if we started with a matrix A that's m by n, and we want to create a homomorphism based on A from V to W, then V is of dimension n and W needs to be of dimension m. Just to review the concepts, I think I've mentioned this before, but let's just state them here again. If the rows of A are linearly dependent, it means the matrix does not have full row rank. The rank of A is less than m in that case, where m is the number of rows. If the columns are linearly dependent, the matrix does not have full column rank, i.e. the rank of A is less than n, where n is the number of columns. Then what's the implication of having these dependencies on our theorem from the previous slide? That's what I'll discuss here. The rank of A determines the dimension of the image or range of the linear transformation F represented by A. If the rows are dependent, rows of A, the image of F is a subspace of W with dimension rank A, which is less than M. If the columns are dependent, the kernel or null space of F is non-trivial. The nullity equals n minus the rank of F, which is strictly greater than 0. So these are the two implications of having dependency. I'll actually give some theorems in a few slides that justify what I'm saying here. I accept I haven't proven anything here. I'm just kind of giving you the facts without any proof. But as I say, I'll get to it in a few minutes. We have an example here of the theorem from the previous slide. We're given a matrix A, and we want to define a homomorphism F based on this matrix. We first note that the two vector spaces need to be of dimension 2, since our matrix is 2 by 2. So let's pick bases. I intentionally picked something other than the standard basis to make it a little more interesting. So for the domain, let's use the vectors 1, 2, and 3, 1. I checked these are linearly independent, so these are a basis. And then for the codomain, I selected these two vectors, and they're much more easily seen that these are linearly independent, form a basis. So we define our homomorphism as follows. It's the matrix A times the representation of a vector V in terms of the basis S, and that'll give us a vector W written in terms of the basis T. So we can take an example here on the right, or just to check, see how things work out. So take the vector V 1 minus 1 and apply our homomorphism to that. So first we need to write V as in terms of the basis, and I worked that out. I mean, what you need to do is write x times 1, 2 plus y times 3, 1 equals 1 minus 1. You get two equations, and then you solve for x and y, which I've done, and this is the result here. So you have minus 4/5 1/2 plus 3/5 3, 1. In other words, it's the coefficients corresponding to these two vectors. It'll give you back 1 minus 1. And so we can write the representation of V with respect to S is minus 4/5 plus 3/5. I just factored out the 1/5 here. I wrote it in this form. And then we can compute the mapping under our defined transformation F. So we take this matrix and we multiply it times this, which I've written in here. I just pulled the 1/5 out, and then I multiplied this matrix times this column vector, and I get 1/5 minus 13, 17 in terms of the basis T. If you wanted to know what this is in terms of the standard basis, we can do that. What this says is that W is 1/5 minus 13 times 1, 0, plus 17 times the vector 0, 2, and that'll give us 1/5 minus 4, 20, 21. This is in terms of the standard basis, if you wanted that information. We could just work in the two bases that we started with, S and T. And just a note here, if we use the standard bases for V and W, then no conversions would be needed. This would be much simpler. You wouldn't need to do any conversion here. And what you got out would also be in terms of the standard basis. You may want to try that as an exercise. It's almost immediate. You just have this times 1 minus 1, you multiply it out, and you'll get a result in terms of the standard basis. For our second example, we're going to use the standard bases. We're given a 2 by 2 matrix, A equals 1, 2, 0, 0. And from our theorem, we can represent a homomorphism by this mapping here. Just the matrix times the vector. I did V transpose because I defined the vector as a row vector. And when you multiply that out, you just get that V1, V2 here, gets mapped to V1 plus V2, 0. And in function form, we can write it like this, which you can see is just of dimension 1. And we know from our earlier work that the dimension of the range, the image space, plus the image of the null space equal the dimension of the codomain. So if this is 1, the dimension of the null space needs to be 1. And I left that as an exercise to actually compute the null space and give a representation for that. What you need to do is set this equals a 0 and then solve for V1 in terms of V2, and you see that you get a one-dimensional space in R2. We have a couple of theorems on this slide. I referred to these earlier, and now I'm going to actually get to them. The first one is the rank of a matrix equals the rank of any linear transformation that it represents. And I'll give you a reference to the proof of that in the information to this video. It comes from an online book that I mentioned here. Then we have another theorem. Let F be a linear transformation from vector space V to W, represented by matrix A. F is onto surjective if and only if the rank of A equals the number of its rows. F is 1 to 1, or injective, if and only if the rank of A equals the number of its columns. And then just a note here, in the second part of the theorem, F could be 1 to 1 with a subspace of the codomain. So in other words, it's 1 to 1 with F of V. All right, so let's look at the proof of the first part. Concerning the surjective part, the dimension F of V, i.e. the rank of F, equals the rank of A by theorem 40. The dimension of the codomain of F, which is the vector space W, equals the number of rows in A. So if the rank of A equals the number of its rows, then the dimension of F of V equals the dimension of the codomain, i.e. F of V equals W and F is onto. Concerning the injective part of the theorem, a linear transformation is 1 to 1, if and only if it is an isomorphism between its domain and its image, F of V. That's true if and only if the dimension of V equals the dimension of F of V. However, the number of columns from A is the dimension of V, i.e. the domain of F. And by theorem 40, the rank of A equals the dimension of V. And then we have in our theorem here where A equals the number of columns. So we get these, in that case, these two are equal. We have a couple of examples here related to the second theorem on the previous slide. In the first example, we have a matrix A that's 4 by 3, and we use that to represent a linear transformation from R3 to R4. If we take any vector in R3 and then multiply it, the transpose of it, A multiplied times it, we get X, 0, Z, Y. The rank of A is 3. We have 3 independent rows. This one here, of course, is dependent on the other 3. But the number of rows in A is 4, so by the above theorem, the mapping is not onto. And we can see that there's no pre-image for the vectors 0, 1, 0, 0 in R4. Since everything in our mapping has a 0 in the second position. However, the rank of A does equal the number of columns in A, we have 3 independent columns, and in fact the mapping is 1-to-1 with the subspace of R4, three-dimensional subspace of R4. Then we can do a second example here. We'll use B instead of A, and you notice the only thing I changed here is I put a 0 here. So as before, the mapping is not onto. Now we have the rank of A is 2, but we have 4 rows. The mapping is also not 1-to-1 since the rank of B is 2, but B has 3 columns. So for example, 1, 2, 3 and 1, 2, 5 both get mapped to 1, 0, 0, 2. In fact, 1, 0, 0, 2 has an infinite number of pre-images of the form 1, 2, and then Z. You can put anything you want in there because it gets mapped to 0. Okay, so our theorem, second theorem in the previous slide, checks out for both of these examples. We have a couple of definitions and then a theorem related to these. A 1-to-1 and onto linear transformation is said to be non-singular. Otherwise, it is said to be singular. So in other words, non-singular and isomorphism mean the same thing for linear transformation. You'll see these used interchangeably. A square matrix A is non-singular if it is the matrix of coefficients of a homogeneous system, AX equals 0, with a unique solution. In other words, A inverse exists. Otherwise, the matrix is said to be singular. So again, we have sort of two terms for the same thing, A being invertible and A being non-singular mean the same thing. Of course, we're talking about square matrices here. Then we have a theorem, 2 parts, a non-singular linear transformation, F from vector space V to W is represented by a square matrix. And secondly, a square matrix represents a non-singular linear transformation if and only if it is a non-singular matrix. In other words, it has an inverse. Thus, the matrix represents an isomorphism if and only if it is square and non-singular. The proof of part 1, assume that F is non-singular and of rank n. By theorem 40, the rank of any matrix A representing F equals the rank of F. By theorem 41 and the fact that F is bijective, we have that the number of rows of A and the number of columns of A each equal the rank of F, in other words n, so A is an n by n matrix. The second part of the theorem, we have the proof here. A square n by n matrix A is non-singular if and only if its row rank is n, which is true if and only if A is of rank n. It's from theorem 23, which I copied down here. And by the definition of the rank of a matrix, which is true if and only if the rank of F is n, i.e. F of V is of dimension n, which is true if and only if F is an isomorphism by theorem 29. The last statement holds true because the domain of F is n-dimensional since it equals the number of columns in A, which we said was n. Related to the previous theorem, for example, any linear transformation represented by A is non-singular since A is non-singular. I checked this. A has an inverse. It's not obvious just by looking at it, but I did check that. And then we have another example here. Any linear transformation represented by B is singular since B is singular. And that's a bit easier to see because B has a column of zeros, and so B does not have an inverse. Okay, so that's the end of this lesson. In the next lesson, I'm going to talk about change of basis. That's something that we'll also need for tensors when we get to that. That'll be another set of lectures that I'll have on tensors, but we'll cover the basic idea of change of basis next.